Okay, let's take a look at another reaction that follows an anti-Markovnikov pattern. And that's the anti-Markovnikov addition of HBr. Now, in order to accomplish this, again, remember because it's an anti-Markovnikov reaction, the bromine is going to attach to the less substituted alkene carbon. In order for this to happen, we need to incorporate an additional reagent in the reaction mixture, and that's this guy right here, which is called a peroxide. So ROOR is a type of organic molecule called a peroxide. Now, in this reaction, you might be tempted to use hydrogen peroxide, but for various reasons outside the scope of the course, that's not going to work out so well. So just remember, you can't use H2O2. Okay, so a couple of examples of peroxides. Here's one. And so what you notice about this is that you have an oxygen-oxygen single bond. This one's called dimethyl peroxide. And then let's do another one if I have room. Let me see if I can make this fit. Okay, here's another one. This one's called benzoyl peroxide. Okay, so some sort of a peroxide you're going to have in there with your HBr. You are also going to need to heat this up. So that's what the little triangle stands for, is heat. Okay, notice that up above it says addition of HBr, so HBr and peroxides. And so it needs to be pointed out here that the reaction only works with HBr. So this anti-Markovnikov result we can only get if we use HBr as the hydrogen halide. We can't get it if we use HCl or HI. All right, so let's look at how the reaction happens. Now, applying the heat that we looked at up above, applying heat has a consequence. And the consequence is that it's going to break the weakest bond in our system homolytically. So applying heat, in this instance, breaks the weakest bond in the system. Now, the system, in this case, just refers to the whole assembly of chemicals that we have in the reaction mixture. And so this bond is going to break homolytically. All right, so let's first understand what's meant by homolytic bond cleavage. So let's say that we have two atoms in a bond, X and Y. If the bond breaks homolytically, what that means is that each of the atoms in the bond, when the bond breaks, each of the atoms gets one of the electrons from the bond. And so what we can do to show that is draw fishhook arrows. So one electron goes with X, one electron goes with Y, and we end up with these guys. So each atom gets one electron. So that's a homolytic bond cleavage. In a heterolytic bond cleavage, one of the atoms would get both of the electrons in the bond. But that's not what's happening. That's not what's happening here. Okay, so this is going to be what's known as a radical mechanism. And a radical mechanism involves the movement of unpaired electrons, so single electrons, and so as such, we're going to be using fishhook arrows to show this. So in the first step, we have a peroxide in solution. And I mentioned to you previously that the oxygen-oxygen single bond is a relatively weak bond. And so that's the weakest bond in the system. So when you heat this, eventually that bond is going to break homolytically. So you're going to get two RO radicals. And remember that these are, an RO group is an alkoxy group. So these are alkoxy radicals. I'll leave it to you to calculate the formal charge on either one of those oxygens so that you can assure yourself that there is no formal charge associated with each of those oxygens. Okay, so the peroxide, the role of the peroxide in the reaction is to generate radicals. So we call the peroxide a radical initiator. Okay, so once you have the radicals, then the radicals can start interacting with the other components of your reaction mixture. So one of the alkoxy radicals is going to encounter a molecule of HBr. And it's going to abstract a hydrogen from the HBr. What that means is that when the radical gets close to the HBr, it's going to cause the HBr bond to break homolytically. So the bromine gets one electron, the hydrogen gets another, and the hydrogen is going to use its electron to form a bond to that oxygen. So we get ROH, or an alcohol, and a bromine radical. Now in a radical mechanism, the steps have names, so they can be classified based on what's happening in the steps. This particular step is what's called an initiation step. And in an initiation step, what's happening is that you're generating radicals from the chemicals involved in the reaction. That is to say, chemicals that are part of the balanced equation for the reaction. So that's an initiation step. Okay, once you have the bromine radical, then the bromine radical is going to be able to interact with the alkene. Now once again, it's going to cause the pi bond in the alkene to break homolytically. So when a radical approaches a compound that's not a radical, usually what's going to happen is that one of the bonds is going to break in the non-radical. So in this case, it's the pi bond. One of the carbons is going to use its electron to bond to the bromine. The other carbon is going to get an unpaired electron, and that's just going to hang out. So the unpaired electron is going to end up on the carbon that can better accommodate or stabilize it. That happens to be the tertiary carbon. So let's draw this, what happens, and then we'll talk about it. Okay, so remember when the pi bond breaks, it's a homolytic bond cleavage, so each of the carbons in the bond gets one of the electrons. One of them is going to use its single electron to bond to the bromine. That's the carbon on the right, the less substituted one. The other one is just going to hang out with its new unpaired electron. Now, we can classify radicals the same way that we classify carbocations. So this is a tertiary radical, and the order of stability of carbon radicals is the same as the order of stability of carbocations, meaning that a tertiary radical is more stable than a secondary radical, and that's more stable than a primary radical. So it's the carbon that can better accommodate or better stabilize that radical that's going to get it. So the tertiary radical forms preferentially. This is what's known, this step is called a propagation step in a radical mechanism. So in a propagation step, what's happening is you're generating new radicals from existing ones. So in this case, the existing radical was the bromine radical over on the left side, and you generated a new, we would call it an alkyl radical. As the product. So this is a propagation step. Okay, so that radical, remember radicals are reactive intermediates, so they're going to react almost as soon as they're formed. One of these guys is going to find an HBr, and cause the HBr bond to break homolytically. So the bromine gets an unpaired electron, and the hydrogen gets an unpaired electron. And the hydrogen uses its unpaired electron to form a bond to the carbon that has the radical in the alkyl radical. So that gives us the product of the reaction. Notice that the bromine is attached to the less substituted carbon from the alkene. And then we can also notice that we generated a bromine radical as part of this step, which makes this also a propagation step. Okay, so in a radical mechanism, you have initiation steps, propagation steps, and then the third type of step, which we don't need to see here because it's not part of the mechanism. But the third type of step generally in a radical reaction is called a termination step. In a termination step, two radicals come together to form something that's not a radical. So let's look at an example that's not part of this reaction. Let's say that we have a pair of these guys. So two separate radicals. And they can bond with each other. And form a neutral species, that is, a non-radical. Now, that's not as common as initiation and propagation steps. Because remember, as soon as radicals form, they're likely to react almost instantaneously. And so the chances of finding two radicals close to one another is going to be vanishingly small. But there are three types of steps, three types of mechanistic steps that we can label in a radical reaction. And so now you know what those are.